Good day everyone, we are from Team 8 and I'm Eng Xin Yi. Today I would like to present about our report problem 3B and this is our BNID diagram. We are consider the two loop and one is at the top and one is at the bottom. And according to the information given, we have Km is equal to 1 and we assume the GV is equal to KB. And first we will find the first order plus daytime model at the top column. And there are total 3 step change and one step change is divided into step up and step down. And first we set the refresh rate as our manipulated variables and we will use the method 2 in graphical method to estimate the parameter, 3 parameter. And first the KP is output over input. Output is basically from the graph, from the process reaction curve, and then the input is the step change. And then the tau is using the formula 1.5 multiplied with the time at 63% of the output minus the time at 28% of the output. And then the theta we'll find by using the time at 63% of the output minus the tau. And then the 3 parameter will substitute into the gain and get a transfer function. And that transfer function is basically XD over R. And the same goes to for the next 2 step change for the feed rate, which is XD over F, and also do for the reboiler duty, which is XD over QR.
For the bottom column, there are 6 first-order plus time delay transfer. By using second method in the reboiler of the step-down process, we obtain a transfer function of GPS equals to negative 0.0528 exponent negative 6s over 11s plus 1 multiple with 10 to the power of negative 4. In the step-up process, we obtain a transfer function of negative 0.0587 exponent negative 7.42s over 22.07s plus 1 multiple with 10 negative 4. In the feed rate, by using second method, we obtain a transfer function of GDS equals to 0.0361 exponent negative 4.74s over 19.73s plus 1. In the step-down process of the feed rate, we obtain by using the second method, we obtain a transfer function of GDS equals to 0.0416 exponent negative 2.64s over 26.48s plus 1. In the reflux rate, the transfer function that we obtain is GDS equals to 0.0288 for exponent negative 6s over 27s plus 1. Next, for the next graph, we obtain GDS equals to 0.032 E exponent negative 11.5s over 16.5s plus 1.
Okay, for the average GS for the loop 1, the top column, we calculate the KP, data average, and also top average to obtain the GP. And for the GD, for in speed rate, we calculate the GS and also for same with the reboiler. For the loop 2, we calculate also the same KP, data average and also tau average to obtain the GP average and also the GS, which the feed rate and the reflux GS equal to GD. And for the stability analysis, we have parameter and also characteristic equation. For the parameter values, we calculate the KP, data average, tau average, and obtain the GM which equal to KM, GV equal to KV, and GC equal to KC since we use the P controller. And for the characteristic equation, we use 1 plus G UL equal to 0 or 1 plus GP, GV, GM, GC equal to 0. And obtain this equation. And we check the general road stability by using the road error and obtain the B1 equal to 1 plus 0.00385 kc. And from this calculation, we managed to obtain this kc which average is equal to negative 261.4379 and bigger than and should not be bigger than 5470.5.
Hi, I'm Azib and I'll be explaining our block diagram. The simulink helps in Ziegler-Nichols tuning. The step response or set point and gain Km was established. The simulink is set to P controller mode only. Then the P value is replaced with the Kc minimum value for stability criterion and root stability. These two are the transfer function disturbance of feed and reboiler in the top column, whereas in the bottom column we have for feed and also for the reflux. These are then followed by the transport delay or FOPDT, where the value of theta is inserted. This in turn helps us in finding the ultimate gain and ultimate period. For offline Cohen-Coon method, the values are calculated using equations from FOPDT. The Kc, tau1, and tau-d for P, Pi, and PID controllers are calculated using the presented equations for both top and also for the bottom column.
So now we proceed to the online turning method for controller by using Simulink. This is for top column. Refer to the trial and error procedure. First, we set the tau t to 0 and then tau I to the largest possible value to eliminate the integral and derivative control actions. Then we set the Kc to a smallest value. And then gradually increase the Kc in small increments until a continuous cycling is occurred. So the continuous cycling is referred to a sustained oscillations with a constant amplitude. So this is the continuous cycling with the constant amplitude. And then when the continuous cycling is achieved in the Simulink, then we can get the KCU show and also the PCU, which is find from the times difference between the amplitude. And then we substitute the KCU and also the PCU to the respective controller by using the formula given. So we can find the Kc for P controller, Kc and tau I for Pi controller, and also the Kc, tau I, tau d for PID controller.
In the loop 2, we set tau d equals to 0 and tau 1 equals to largest possible value in order to eliminate an integral and derivative control action. Then we set Kc to the smallest value. When continuous cycling is achieved, we obtain the value of Kcu and PCU. Kcu obtained are negative 267.629, while PCU obtained is 23.1 second. In the P controller, the value of Kc obtained is negative 433.82 kcal over mean. While in Pi controller, we obtain the value of Kc equals to negative 120.43 kcal per min, while tau 1 we obtain 11.55 minute. In the PID controller, we obtain the value of Kc equals to negative 160.58 kcal over min, while tau 1 we obtain is 11.55 minute, tau d we obtain is 2.89 minute. Then we compare the method of offline Cohen-Coon and online Ziegler-Nichols. From this table, we can see that the Kc obtained are in the range of the Kc calculated in stability analysis. We can say that in loop 1, PID controller is preferred because it has the higher value of Kc. When Kc increases, the speed of response increases. In loop 2, Pi controller is preferred because it has the higher value of Kc. That's all from Team 8. Thank you.